Welcome to our deep dive, everyone. Get ready, because we're going to tackle a pretty huge question today.
A big one, for sure.
How on earth did we go from, counting on bones
Yeah.
to having these crazy, powerful computers, more power than they had for the Apollo missions, just in our pockets?
It really is a mind-blowing journey when you think about it, thousands of years, and it all comes down to humans always wanting to make things that, help us do more,
Yeah.
understand better.
Yeah, like control things.
Control, exactly. And that drive, it takes us all the way to the digital age we live in now, which is pretty wild.
And get this, it doesn't start with some fancy silicon chip or circuits or anything like that.
Nope.
It starts with bone, straight up bone.
You got it.
The Lobombo bone found in Africa. This thing is 35,000 years old?
At least.
Can you imagine counting on a baboon bone?
It wasn't exactly a pocket calculator, that's for sure.
Uh-huh.
But those 29 notches, they were probably for keeping track of the moon's cycles. When's the full moon going to be?
Yeah. So like a lunar calendar.
Exactly. And it shows you, even way back then, humans were watching the world, trying to figure it out.
Yeah.
And then they had to write it down somehow. Then you've got the Ashango bone, could be even older. Some people think that was used for, actual math.
Really? Math on a bone?
And looking at the stars, too. People have been doing that forever.
That's incredible. So we go from these, early tools to something we all know. At least I remember playing with one as a kid, the abacus. I never really thought of it as anything more than a toy.
Right.
But it's actually super important, isn't it?
Way more than a toy. It's like the very first portable calculator. And get this, they're still used today.
Really?
Especially in some parts of the world, for teaching kids math.
Why is that? You'd think with phones and computers everywhere, who needs an abacus?
Well, it's because of how you use it. You're moving those beads around, it's hands-on.
Oh, I see.
Helps kids understand numbers in a different way than just punching them into a calculator.
That makes sense.
It's like they're feeling the math,
So simple tools can still be the best for learning. But obviously, over time, we needed more powerful tools.
Of course. The more we understood about math and the universe and all that, the more we needed better tools.
Yeah. And that leads us to ancient Greece.
Ah.
And the Antikythera mechanism.
Yeah, that is an incredible piece of history.
It really is. It was found in a shipwreck, right?
Yep, back in 1900.
So 2,000 years ago, they had this thing.
And it's not just any old relic. This is a serious analog computer. All these intricate gears, and they used it to track where the stars and planets would be, even predict eclipses.
I can't even picture how they made something that complex back then. Must have seemed like magic.
The Greeks, they were amazing engineers. But the Antikythera mechanism, it wasn't just some random invention. It's part of a long line of tools they made for understanding the sky, like planispheres, the star charts and dioptras for surveying and stuff.
So they were always innovating, building on what came before.
Exactly. A continuous thread, you might say.
That's awesome. But what happened after the Antikythera mechanism? Did things just stall out for a while?
Oh, not at all. People still wanted to calculate faster and better. That's where the mechanical calculators come in.
In the 1600s.
Yep. And Blaise Pascal, the philosopher, he was a big part of that.
I didn't know he was an inventor.
Well, he was a brilliant guy, did all sorts of things. And in 1642, he built the Pascaline. That was the first mechanical digital calculator.
How did that work?
The clever part is this thing called the transmission mechanism. It let you carry over numbers when you were adding, like when you go from 9 to 10, it carries the 1 over to the next column.
It's still how calculators work today, right?
Exactly. That idea from the 1600s is still in use. But Pascal wasn't the only one working on this stuff.
Yeah.
Gottfried Leibniz, another super smart guy from the 1600s, he wanted to do more than just basic math.
Okay.
So he built the stepped reckoner. It could do all 4 operations. Add, subtract, multiply, divide.
Wow. A multitasking calculator from the 1600s.
Pretty impressive, huh? But these calculators, they weren't programmable, not like computers today.
Right. So how did we get from those to something that could be programmed?
That's where the Jacquard loom comes in. This thing was invented in 1801, and it used punch cards to tell it what pattern to weave.
Like a pre-programmed design.
Exactly. And that idea, using a series of instructions, that's what makes computers work,
Yeah. So the loom itself wasn't a computer, but it gave people the idea for how to make them programmable.
That's fascinating. Speaking of big ideas, what about Charles Babbage? He's a pretty legendary figure in computing history.
Oh, Babbage was a character. He'd have these big parties in London back in the 1800s. and invite all the smartest people he knew.
It sounds like a fun time.
It wasn't just partying, though. He'd show off his ideas about these incredible machines he was designing.
Like the difference engine and the analytical engine, right?
Those were way ahead of their time. The difference engine, it was supposed to automatically calculate and print math tables. Math tables. Sounds a bit dull.
Maybe, but think about all the calculations involved. And the analytical engine, that was even more ambitious. It was supposed to be a programmable computer that could do all sorts of things. It had a mill for doing calculations, a store for memory, even a system for printing out the results.
Printing in the 1800s, that's crazy. But if these things were so advanced, why didn't he ever actually build them?
That's the sad part. The technology back then just wasn't good enough. Too complicated for Victorian engineering.
So it was all just theory.
Luckily, he wrote everything down. Designs, notes, the whole works. And guess what?
What?
People actually built the difference engine in the printer based on his plans, much later, of course.
They did.
And they worked, just like he designed them.
Wow, that's incredible. A true visionary. But even though his machines weren't built in his lifetime, his ideas were important, right?
Hugely important.
Right.
And the work he did with Ada Lovelace, another pioneer, it laid the foundation for everything that came after.
Yeah. So we move into the late 1800s and early 1900s. Things are starting to pick up speed, right?
Oh, yeah, things are about to get really interesting. It's like all these ideas, they've been simmering for years, and now they're about to boil over.
And that's where IBM comes in, right? The story of Herman Hollerith and his punched card tabulating machine.
Now, that is a story that takes us from inventors tinkering in their workshops to the start of the modern information age. And it all begins with, believe it or not, the 1880 U.S. Census.
The census? Okay, I'm intrigued. How does counting people lead to IBM?
Well, it all started with a problem, a really big problem. Imagine trying to count millions of people, and then you have to organize all that data.
Yeah.
The 1880 census, it took 7 years to process.
7 years? You're kidding. That's ridiculous.
They knew they had to find a better way, especially with the population growing so fast.
I bet. So what did they do?
That's where Herman Hollerith comes in. Brilliant guy, a statistician and inventor. And you know what inspired him?
Let me guess. The Jacquard loom.
Bingo. He realized those punch cards, they weren't just for weaving patterns. You could use them to store information about people.
Ah, so instead of threads, you've got holes representing like age, job, that kind of thing.
Exactly. And he built this machine, the tabulating machine, to read those cards.
How did that work?
It used electricity, which was pretty new at the time. Each hole in the card, it would let a metal pin go through, complete a circuit, and bump up a counter.
So like more holes, higher count, you know what I mean?
Exactly. It was revolutionary.
Yeah.
The 1890 census, with Hollerith's machines, it was done in 3 months.
Wow, talk about efficiency.
Saved the government tons of money and time. And Hollerith's company, well, it eventually became part of IBM.
No way. From census counting to one of the biggest tech companies in the world.
It's a pretty amazing story, isn't it?
It really is. Shows how innovation can come from anywhere. But we're not quite to the age of computers as we know them, right?
Not yet. There's a few more steps along the way. Some amazing people bridging the gap between those mechanical systems and the fully electronic computers we know today.
Okay, let's hear about them.
One of them was Vannevar Bush. In the 1930s, he built this massive machine called the differential analyzer.
Big as a house.
Pretty much.
Yeah.
Filled a whole room. It was all gears and shafts and wheels, and it was designed to solve these really complicated equations, differential equations.
I'm getting flashbacks to calculus class.
Huh. But these equations, they're super important for scientists and engineers, figuring out stuff about physics, astronomy, building things.
So it was like a super calculator for really smart people.
That's a good way to put it. It could handle way more variables than a human could. It was a huge step forward for doing science and engineering.
But I thought we were talking about electronic computers. Was this differential analyzer electronic?
It was mostly mechanical, but it did use some electronic components for controlling it and making the signal stronger.
Ah, so like a hybrid.
A fascinating step in the evolution, you might say.
Makes sense. But wasn't there a German inventor working on something similar? Around the same time?
Oh, absolutely. Konrad Zuse. He was a civil engineer, and he was building his own computers called the Z computers over in Germany.
In the 1930s?
Late 30s, early 40s. And his work, it was revolutionary. His Z1, finished in 1938, is considered the very first programmable computer that used Boolean logic and binary representation.
Whoa, hold on. Boolean logic. Binary. Can we break those down a bit?
Sure. Boolean logic, it's a way of thinking about things as true or false. Like a light switch is either on or off.
Yeah, okay.
That's how computers make decisions, basically.
Got it.
And binary, that's just using zeros and ones to represent information. Like instead of writing 5, you'd write 101.
So Zeus was using the same kind of language that computers use today, but his machine wasn't electronic.
Not entirely. But he was thinking the right way. And in 1941, he built the Z3. That was the first fully functional, programmable, automatic digital computer.
That is a lot of adjectives. But if it was still using relays and stuff, it wasn't truly electronic, right?
Good point. It was still electromechanical, but it showed what was possible. Zeus proved that you could build a programmable computer, even with the technology of the time.
That's incredible. And it all happened while World War II is going on.
Yeah. Speaking of the war, that takes us to the top secret world of code breaking.
Ooh, spies and secret missions.
You bet. This is where we meet Colossus, a machine that changed the course of the war.
I'm all ears.
During the war, the Germans were using this super sophisticated encryption machine called the Lorenz cipher to send secret messages. The Allies, they were desperate to crack the code.
Wait, I thought Enigma was the German code machine.
That was one of them, and the British had already cracked that with their bomb machine. But the Lorenz cipher was even more complex, used for the really important messages.
So breaking this code was super important.
Absolutely. And that's where Colossus comes in. It was the first fully programmable electronic digital computer built by the British specifically to break the Lorenz cipher.
The first electronic computer. Wow, what did it look like? One of those giant room-filling machines.
It was big, that's for sure. Filled a good chunk of a room, and it used thousands of vacuum tubes, those glass things that control electricity. And here's the thing, Colossus was top secret for decades.
Really?
Yep, we didn't even know about it until the 1970s.
Why all the secrecy? Even after the war?
Well, they didn't want to give away their code-breaking secrets. Plus, there were worries about what other countries would do if they knew how advanced the Allies were.
So this amazing invention was hidden away for years? That's kind of sad.
It is, in a way. But luckily, they were able to rebuild Colossus in the 1990s, based on the original plans.
Wow, they rebuilt it from scratch.
It was an incredible feat of engineering. It means we can now see this machine in action and really understand how it helped win the war.
Amazing. It shows that sometimes the most important innovations happen in secret. But with Colossus, we see electronic computing really coming into its own. What about other people working on electronic computers around that time?
Well, over in the U.S., John Vincent Atanasoff was having his own light bulb moment. He came up with the idea for the Atanasoff-Berry computer, or ABC.
The ABC.
Yep. And this is where the story gets a bit controversial.
Oh, I love a good tech rivalry. Tell me more. So we've got a top secret code-breaking computer in England and a physics professor having a breakthrough in America. Sounds like the race to build the first electronic computer is heating up.
It definitely was a time of incredible innovation. And remember, back then, communication wasn't what it is today. These discoveries were happening on opposite sides of the world almost simultaneously. It's amazing.
Tell me more about Atanasoff's big idea. What made the ABC so special?
Well, Atanasoff was a professor of physics at Iowa State College, and he was getting pretty frustrated with the calculators they had back then.
They were still mostly mechanical, right?
Yeah, and for the kind of research he was doing, they just weren't cutting it. Too slow, not powerful enough. So the story goes, he's driving one night, just thinking about this problem, when bam, inspiration hits.
I love those moments. It's like a lightning bolt.
He realized he could use electronics to build a much better computer. Specifically, vacuum tubes for calculations and capacitors for memory.
Vacuum tubes. So was the ABC the first electronic computer then?
Well, that's where the debate comes in. See, the ABC, which he finished in 1942, it did use these electronic parts, and it used binary, like Zeus's Z computers, but it wasn't fully programmable in the same way that later computers would be.
Ah, so it was an important step.
Absolutely.
But not the final destination.
Yeah, a crucial stepping stone. But those innovations using electronics and binary, they were hugely influential. And that's why there was this big patent dispute later on.
Oh, right. You mentioned that earlier. Who was Atanasoff fighting with?
The creators of the ENIAC, which we'll talk about in a sec. For years, the ENIAC was considered the first electronic computer.
So they were both claiming to have invented it.
Basically, yeah. And in 1973, a court ruled that the ENIAC's design was heavily based on Atanasoff's work, giving him credit for his contribution.
Wow. A legal battle over computer history. So Atanasoff gets his due, But the ENIAC was still a big deal, right?
Oh, absolutely. The ENIAC, it was unveiled in 1946, and it was this massive undertaking. Over 17,000 vacuum tubes took up a whole room.
I've seen pictures. It's like something out of a sci-fi movie, all those glowing tubes.
It was mind-blowing for the time, 1,000 times faster than anything before it. And it could do these really complex calculations, like figuring out the path of artillery shells for the army.
So a powerful machine, but I bet it wasn't very energy efficient.
You got that right. Vacuum tubes, they used a ton of power and they burned out all the time. And programming it, forget it. You had to physically rewire the circuits, could take weeks just to get it to do a new task.
Sounds like a nightmare.
Not exactly user-friendly, but it proved that you could build these large-scale electronic computers, and that opened the door for everything that followed.
Yeah. And the ENIAC's creators, they didn't just stop there, did they?
Nope, they went on to found a company that would build UNIVAC.
UNIVAC, that's the one that predicted the election, right?
The 1952 election, Eisenhower versus Stevenson, UNIVAC, using just a small sample of voters, got it right.
That must have blown people's minds back then.
It was a huge deal.
Yeah.
It showed how powerful computers could be for analyzing data, even predicting the future.
Yeah.
But it also meant that other companies were jumping into the game. IBM, which had been the big player with their punch card systems,
Right.
they were facing some serious competition now. The computer industry was becoming a major force.
So we go from those big clunky machines like the ENIAC to something that can predict elections with UNIVAC. Things were moving fast, but these computers were still huge and expensive, right? Not exactly something you'd have at home.
That's a great point, and that's where transistors come in. They changed everything.
Transistors. I know they're important, but I'm not really sure what they are.
Imagine a tiny switch, so small you can barely see it, that can control the flow of electricity.
Okay.
That's basically a transistor. It can amplify signals, switch them on or off. It's the heart of all modern electronics.
So how did they change computers?
Remember those vacuum tubes? Big, hot, unreliable.
Yeah.
Transistors could do the same job, but they were tiny, used way less power, and lasted much longer. It was revolutionary.
So you could build much smaller, more efficient computers.
Exactly. The transistor revolutionized everything, but especially computers. It made them smaller, cheaper, more reliable. That's what paved the way for personal computers.
Wow, the tiny transistor, the unsung hero. But there's still a gap between transistors and the computers we have now. What came next?
The integrated circuit, or microchip. It's basically putting lots of transistors and other components all onto a tiny chip of silicon.
So instead of wiring all those transistors together individually, you've got them all packed onto one chip.
Exactly. And this was huge. The integrated circuit, invented in the late 1950s, made electronics even smaller, more complex, and cheaper to make. It led directly to the microprocessor.
The microprocessor, the brain of the computer on a single chip. This is where it all comes together, right?
You got it. The microprocessor, invented in 1971, put an entire CPU, the central processing unit, onto one little chip. Amazing.
1971. That's not that long ago, considering what computers can do now.
I know. It's incredible how fast things progressed.
And it's all thanks to that exponential growth we talked about before.
Right, Moore's Law. Gordon Moore, one of the founders of Intel, predicted that the number of transistors on a chip would double every 2 years or so. And he was basically right.
So we went from a few thousand transistors to billions on the chips we have today.
And with each doubling, computers get more powerful, more efficient. That's what's driven the whole digital revolution.
It's like a chain reaction. And that leads us to the personal computer. Finally, computers for everyone.
Right. The PC, it came about in the late 70s, early 80s, thanks to all these innovations coming together. The microprocessor, integrated circuits, and user-friendly operating systems.
And we can't forget about Apple.
Absolutely. Apple, with their focus on making computers easy to use and beautiful to look at, they played a huge role in making PCs popular.
But they weren't the only ones. Didn't IBM come out with a PC around the same time?
They did. The IBM PC launched in 1981. And it was a game changer because it was much more affordable than their previous computers. Businesses and regular people, they could actually buy these things now.
And wasn't there something special about the operating system?
There was. They partnered with this small company called Microsoft to make it.
Microsoft. Wonder what happened to them.
Huh? That's a story for another day. But that partnership, it shaped the entire computer industry.
So from counting on bones to the Antikythera mechanism, from Babbage's amazing ideas to Colossus cracking codes, from transistors to the PC, it's been an incredible journey.
It really highlights how creative and persistent humans can be. We have this drive to keep innovating, to solve problems, to push the limits of what's possible.
And it's not over yet. Who knows what incredible inventions are just around the corner?
Exactly.
Yeah.
But it also makes you think. As computers get more powerful and integrated into our lives, what does it mean to be human? Are we going to see computers that can think for themselves, like HAL 9000?
That's a big question. And it all started with a simple desire to count and calculate. From ancient bones to artificial intelligence, it's all connected. Thanks for joining us on this deep dive into the fascinating world of computers.
It's been a pleasure.
Keep those questions in mind, and we'll see you next time for another deep dive.